Thanks for the introduction. Thank you all for being here. I know it's been a really long week, so I appreciate all the turnout. All right, so I'm excited to talk about joint work with Alex Lombardi and John Wright. Let's get to it. So in complexity theory, we typically think about computational problems as having a classical input and classical output. So I mean problems like given a three-stat formula, decide whether or not it's satisfiable, given a graph G, output some Hamiltonian cycle. And this is even true for quantum complexity classes like BQP and QMA. So what I mean by that is that the canonical QMA complete problem, local Hamiltonian, is a problem where you're given a classical description of a local Hamiltonian, and you produce a classical output bit indicating whether that Hamiltonian has a low energy ground state. And so even though this problem is sort of about quantum states and about quantum computation, it's fundamentally a classical input, classical output question. On the other hand, many important computational problems have quantum inputs and quantum outputs. So just some examples, state tomography, the problem is you're given many copies of some quantum state and you have to output some classical description of the state. Quantum error correction, you're given as input some noisy quantum error correcting code word. Or this state distinguishing problem. There's a pair of mixed states, row 0, row 1, and you have some implicit description of these mixed states. And in the problem, you're going to be given one of these mixed states at random, and the task is to distinguish which one you got. These problems show up in many other places, including in physics and the study of quantum gravity. So you can ask, what can we say about the computational hardness of these inherently quantum problems? Well, typically, the standard procedure for understanding computational hardness of any problem is basically to try to reduce it to some well-studied standard complexity class. So you can ask, does my problem become easy if I'm given an oracle for NP, or an oracle for P space, or some other complexity class? But for some quantum problems, it's not clear if the standard approach really works. So for instance, for the state distinguishing problem, where there's a pair of mixed states implicitly specified in some way, and you have to distinguish which one of the two that you're given, it's not clear if there is any oracle that makes this easy. So really, even if I give you an oracle that can solve the halting problem instantaneously, it's not clear how you use that oracle to make this computational task any easier. So this raises the question, does standard complexity theory, have the ability to capture these inherently quantum problems? So let me sort of rephrase this question a little bit. When I talk about solving a quantum problem, what I really mean is implementing some sort of unitary transformation. And in contrast, what I'm saying is that standard complexity theory is all about the computational hardness of implementing functions, which are maps from classical strings to classical strings. And so to apply complexity theory to understand the computational hardness of implementing some unitary, what you really want is some reduction that reduces the task of implementing that unitary to the task of implementing some function. And so this brings up the unitary synthesis problem, originally posed by Aronson and Kuperberg in 2006. They ask, is there a generic reduction that works for every unitary? So let me state it a little bit more formally. The way that they phrase the problem is as follows, and I'll take a whole slide to unpack this, so don't worry if it's a bit confusing. They ask, is there an efficient oracle algorithm A that can implement any n-qubit unitary U to some precision, given some function f? So here's what we're asking. We're asking, does there exist some efficient oracle circuit A? It could look like this. And by efficient, what we mean is that the total number of qubits that it acts on is just a polynomial in n, so it's L qubits. And the total number of gates that we use, both some fixed gates from some universal gate set together with oracle gates, the total number of gates is poly in n. And so we're fixing some sort of universal oracle algorithm A, and then we're given some n-qubit unitary. And the question is whether it's always possible to pick some function f that possibly acts on up to L bits, some classical function f, and sort of plug in the corresponding phase oracle for f. So I'm going to plug in O sub f being the unitary that just writes f into the phase of its input. And the question is there always a way to pick some f such that this circuit implements the unitary in the sense that the channel it's implementing from the input to the output registers is close in some distance metric to the desired unitary? So very, very little is known about the unitary synthesis problem. Um, on the upper bound side, the total number of queries that's required, the best we know is an algorithm that takes 2 to the n over 2 queries. So exponentially many queries. So definitely not efficient. And on the lower bound side, we have no query lower bounds. All that we know is that is a result from the original paper proposing the problem, where Aronson and Kuperberg proved that there is a one query lower bound, but for a very restricted class of Oracle algorithms. So I want to say a little bit about why I think it's been so difficult to prove anything on the lower bound side for the unitary synthesis problem. I think the one reason is that counting arguments don't seem to get you very far, and they're kind of the most natural thing you might think to try when you see the unitary synthesis problem. Because you might think, well, there's a lot of unitaries and potentially far fewer functions, so maybe you just don't have enough degrees of freedom to be able to implement all unitaries. And while it seems reasonable, it's not quite right. And the reason is that, like, up to some epsilon precision, you really only have 2 to the 2 to the 2n different n-qubit unitaries, and the number of functions you can have on L bits, on L being some poly and n bits, is 2 to the 2 to the L. And so you can't do a counting argument once L is bigger than 2n. So you certainly have enough degrees of freedom to implement all unitaries. So if there's a lower bound, it must be for a more subtle reason. And the other reason is sort of a conceptual reason, which is that even one query algorithms, like the moment you make one query, this is a really, really powerful class of algorithms. So maybe one query sounds kind of pathetic, but it's one query to any function you want. So these kinds of algorithms can instantly solve the halting problem. They can solve any classical input, classical output problem. And actually, as you saw in the last talk, they can solve a large fraction of quantum problems as well. They can solve any quantum problem where you have a classical input and the task is to output some quantum state. Okay, so what we show in this work is that there is no efficient one-query Oracle algorithm for the unitary synthesis problem. And actually, we go a little bit beyond ruling out just the efficient ones. We rule out any Oracle algorithm that queries a function on inputs of bounded length, where the length bound is actually pretty large. It's all the way up to little o of 2 to the n. But beyond this, the algorithm can have unlimited size and unlimited space. And I just want to point out that some bound on the functions that you can query is necessary, because if the functions take inputs of length 2 to the 2n, it turns out that there's a way to adapt the Bernstein-Vazirani algorithm to make a single query and learn an entire classical description of U instantly. So for the rest of this talk, I just want to hopefully cover two things. First, I'm going to connect unitary synthesis to a different problem, breaking quantum cryptography. And in the second part of this talk, I'm going to hopefully cover a very special case of our proof. Okay, so the way that we prove this result about unitary synthesis, and indeed how the project actually started, was we were looking at pseudorandom states. And for the purpose of this talk, I'm going to define a pseudorandom state as follows. It's an efficiently constructible family of n-qubit states, PRS sub k, where the total number of states, capital K, is far, far smaller than the ambient dimension, capital N. And you want the following property, that no efficient adversary can distinguish between the following two distributions on states. The first distribution is I sample a random PRS state and give you PRS sub k. And the second distribution is just a har-random n-qubit state. And just to be clear, I'm only talking about this one copy definition. I'm not going to give you multiple copies of the state. I'm just giving you one copy. But just note that this is certainly a computational assumption, that this is something that you can break inefficiently simply because the PRS states lie in a low-dimensional, capital K dimensional subspace. So the existence of this cryptographic primitive, the existence of this notion of a PRS would have far-reaching consequences in cryptography. It implies quantum bit commitments, zero knowledge, multi-party computation, a whole host of really interesting protocols. And so a fundamental question in quantum cryptography is to understand how hard is it to break a PRS? And the answer we give in this work is that, at least in a black box sense, it's probably harder than computing any function. So that brings me to main result number 2, which is we show that relative to a random oracle R, there exists a PRS family that is secure against any oracle adversary that makes one query to an arbitrary function, where the function that it queries can depend arbitrarily on this random oracle R. And I want to note that this result actually implies our unitary synthesis lower bound as a corollary. So this is actually what we prove. We prove this, and the unitary synthesis lower bound follows immediately. And the reason that that's true is because if you show that a certain class of algorithms can't break particular PRS, then necessarily there are some unitaries that this algorithm cannot implement, right? Because just because there exists a way to break the PRS information theoretically, and so we're saying that those unitaries cannot be efficiently synthesized. Okay, so how does our result actually work? Our PRS family is just going to be a collection of capital K random binary phase states. So a binary phase state is a state that you can associate with any Boolean function h. So I'm going to find the binary phase state psi sub h to be the uniform superposition over all x, where the coefficient of ket x is just determined by the value of h of x. So it's either plus or minus 1. And our PRS family is just going to be this collection of psi sub rk's, where each rk is a random function. And so the adversary's task is going to be to distinguish psi sub rk for a uniformly random k, or psi sub h, a totally fresh random binary phase state. And what it gets to do in order to distinguish these two distributions is we're going to give it one query to an arbitrary function f that can depend on the description of all these binary phase states. It can depend arbitrarily on capital R. Okay, so towards sort of showing you what our proof ideas look like, let me first say, what does a one query adversary look like? Like, what can it actually do? Well, in general, it'll take this input psi, and the first thing it can do is initialize some number of ancilla qubits, 0. And at this point, now it has L total qubits. And then it can do some arbitrary fixed unitary transformation, I'll call it U. And then after that, it makes its query to this phase oracle O sub f. Since it'll be relevant a little bit later, I just want to remark that this phase oracle, if you think of it as a matrix, it's a diagonal matrix with pluses and minus ones on the diagonal. So maybe just keep that in mind for 5 minutes from now. And finally, after the oracle query, it gets to do another fixed unitary and then a measurement. And then the measurement will say whether it's going to guess whether it's a PRS or a random. And so throwing away all the details, like really what's just happening here is it's a unitary, an oracle query, and then some projector. And so the probability that this adversary outputs, or this adversary outputs 1 on a given state psi, is just the norm squared of pi applied to OF applied to U applied to psi tensor 0. And so the adversary's maximum distinguishing, or the adversary's distinguishing advantage for a fixed PRS family specified by capital R is just the difference in these two expectations, where the first one is the expected probability that the adversary, or it's just the probability the adversary outputs 1 in the PRS case, so when it receives a random psi sub rk. And the thing I'm subtracting is the probability the adversary outputs 1 when it's given a truly random binary phase state. And so what you want to show is that for any fixed adversary strategy, so the adversary will fix some unitary and some projector pi, that if you then sample a random capital R, so the random collection of binary phase states, then no matter what function the adversary picks, this quantity cannot be too big. In particular, it's going to be negligible in little n. So the entire technical part of this paper is just bounding this optimization problem. And it turns out this problem is quite subtle. So just in 2 bullets, what do? What we show is that there is a very carefully chosen spectral relaxation of this quantity that gives an upper bound of this in terms of the operator norm of a certain random matrix. And then we bound this norm by appealing to a phenomenon called matrix concentration. So if that was all gibberish, the last 5 minutes of this talk will hopefully demystify that just a little bit. So I'm going to do a very special case of our proof and show you like a little bit of how this idea works. So for this, I'm going to focus on a very, very special, kind of pathetic class of one-query adversaries that you could actually rule out with a counting argument. But I'm going to do it here in a different way so that you can see how our real technique works. So for this class of adversaries, I'm going to assume that there are no ancillas, and the first unitary is actually the identity. So I'm getting rid of the ancilla, getting rid of that U, and the adversary will just receive its state, do some phase query, some phase oracle at this point, and then do some projector pi. And so the probability outputs 1 is now the simpler expression, and our task is to bound this distinguishing advantage here. I've just expanded out the norm squared into a sandwich. So the technical tool we're going to use is something called matrix concentration. So this is sort of a matrix analog of a kind of scalar Chernoff bound. So let me just recall that the scalar Chernoff bound says is that if you have a bounded random scalar x, so absolute value is bounded by a constant, and then you're given capital K IID samples of x, so x1 through x capital K, and you take the average of these samples. Well, this average of these samples is not going to be too far from the true expectation. In particular, it's going to be about 1 over square root of k far with high probability. So matrix Chernoff is a generalization of this to matrices. And it says that if X is a random symmetric L by L matrix with bounded operator norm, so operator norm meaning the largest eigenvalue of this matrix, then if I take capital K IID samples of this random matrix and I average those together, then this is really close to the expected random matrix in the sense that if you take their difference, then that difference matrix has bounded operator norm. In particular, it's something like this 1 over square root of k in the scalar case, but then you pay this multiplicative square root of log the dimension factor in the numerator. Okay, so matrix Chernoff is what we're going to use, but it's not so like immediate. The reason is that if you look at the quantity we want to bound, which is the thing on the top, and sort of compare and contrast this to what's going on with matrix Chernoff. Here I've rewritten the matrix Chernoff bound a little differently. I've expanded out the definition of operator norm and turned that into a max over unit vectors. Well, something like there's a bit of a mismatch here, where in the top we have this maximization, like the quantity you're maximizing over, or the thing that you're maximizing over is the matrix in the middle of the expression, and the capital K random things are these vectors in the outside of the expression. And in matrix Chernoff, what you have is you have these random matrices in the middle of the expression, and the thing you're maximizing over is this unit vector on the outside of the expression. So the question is, how do you make use of matrix Chernoff to say anything about the expression at the top? And I've picked this example to make it actually quite easy. So for this example, it's going to this special class of adversaries. It's going to turn out that we can very easily refactor this expression to be exactly the form that a matrix Chernoff will allow us to finish the proof. So let me show you how that's done. And I'm just going to do that for a single term because all of the terms are identically distributed. So this is like a single term in the adversary's distinguishing advantage. And all we need to do is realize like what exactly is a form of psi sub rk. So remember, like psi sub rk is this binary phase state whose phases are determined by this function r sub k. And I can decompose this binary phase state into a diagonal matrix where all the phases are written on the diagonal times a fixed unit vector. In particular, it's going to be the uniform superposition, right? So now let me call that diagonal matrix d sub rk and call the uniform superposition plus sub n. I can just write this out. And then you realize that, well, we have this d sub rk, which is a diagonal matrix, and it's sitting right next to this phase oracle O sub f, and that's also a diagonal matrix. And so we can actually just commute them past each other. And now this expression is of the form we wanted, right? Now we have this drk pi drk in the middle. That's a random matrix. And we've moved the thing we're maximizing over, this f, to the outside of the expression. We've moved it to the vector. So I can do this to the whole expression and pull out this O sub f times plus n all the way to the outside. And just notice that this is always a unit vector. Like no matter what function is chosen, this is just a unit vector on the outside. And so this quantity is at most the spectral norm of this matrix in the middle. And this is precisely what you can bound with a matrix Chernoff argument, simply because this matrix drk pi drk is always bounded in norm. Right? It's a projector conjugated by a unitary, so its norm is 1. So extending this proof to the general case requires quite a bit more work. And the issue is that in the general case, the adversary can perform some isometry before it does the query. So the isometry corresponding to adding some ancillas and then doing a unitary. And the problem with having a general isometry is that the isometry sits right in the middle of this DH and this OF. Right? The whole point of the previous argument was that I could commute those two operators past each other and move all the randomness to the middle of the expression and move the thing I'm optimizing over to the outside. But now this V gets right in the middle of the two things I'm trying to commute past each other. So that's kind of the main technical challenge that we had to resolve. And in just one bullet, our solution is that we notice that by taking advantage of like really nice concentration properties of binary phase states, you can show that actually the state v times psi h can be factored as some diagonal matrix times a particular fixed v-dependent unit vector. And once you do this decomposition, you can basically make the same proof strategy as before work, where you move this like random diagonal matrix to the inside of the expression and then do a spectral relaxation. Right, so conclusion, this like one query lower bound, I think suggests that the task in general of implementing a unitary or breaking quantum cryptography is harder than any classical problem in the sense that it's unlikely that there's any black box reduction. And another sort of takeaway from this is that there's potentially no like complexity theoretic barriers to unconditionally proving hardness for many quantum tasks. So if someone came out tomorrow with a proof, like an unconditional proof that pseudorandom states existed, like computationally secure one copy pseudorandom states existed, this would not separate, like this would not resolve any long-standing complexity theoretic conjectures as far as I'm aware. So I think that the next step is that well, we strongly suspect that this lower bound can be extended. That the resolution is probably not that there is a two query algorithm, but probably that there is just a better proof technique or a more powerful analysis that can handle the general case, where the adversary can make any polynomial number of queries to the function. We've been trying really, really hard. This like the past year of my life has been thinking about this conjecture. And really the challenge is that it's just very, very hard to find a good spectral relaxation beyond one query. All right, thanks so much for listening.
Questions? Yes.
So, thank you for nice talk. So you showed that for single, if the adversary get a single copy of state, no classical oracle can break this. But on the other hand, if you get enough polynomially many copies of state, in this case, PP oracle is enough. Do you have any idea about the situation in between these two cases?
Yeah, good question. So Tomoyuki is pointing out that it's actually known that if you change the definition of a PRS and you consider the multi-copy version, where the adversary gets any polynomial number of copies of the state, well, then it's known that you can actually break the security of this object with access to a PP oracle. And what I'm claiming is that, and that's actually in one query as well. And I'm claiming that one query doesn't suffice for just given one copy of the state. I am very sure that this proof extends to getting constant many copies of the state. I'm not too sure like beyond that. The cutoff might start being around like log or something, number of copies of the state. And then beyond that, I don't actually know sort of what that curve looks like. Yeah, but I guess morally, like what's going on in the multi-copy attack is that once you have enough copies of the state, you can sort of kind of do like a tomography attack where like that's enough to sort of learn some classical information and turn this like quantum distinguishing task into a problem where your classical oracle becomes useful. But like once you don't have enough if you don't have enough copies, it's hard to do this transformation.
Hi, very nice talk. Thank you. Early on, you said some limit on the size of L, that if L is too large, then there is a single. So does that only apply in the unbounded algorithm case? Or like, did you say that there's a limit on L even if your algorithm has to be efficient?
Oh, I guess if the algorithm is efficient, then it can only query L when L is like poly n. L is like it can't even write it down what it's querying F on.
Sure.
Right?
So the limit was exponential, not just polynomial.
So if you just care about efficient oracle algorithms, like ones that are, I guess when you think about oracle algorithms, you often like relax your typical notions of efficiency and you only charge them for queries, right? Okay. And this L is sort of like what is the size of your query? Like L is intuitively like the number of bits of information you can get from a query. So I guess if you only care about like oracle algorithms that are also efficient in like the standard sense, then you don't need to go beyond L being poly and n.
Yeah, and that is enough, you're saying.
It's enough to rule out like that, but you know, you may as well, if your proof technique works for it, just go and rule out like larger L's if you want.
Yeah, I had another question, which is, do we really know any useful or do we know any algorithms that do use more than one query, like more than one query to a classical oracle? Why would you need
like in life or like for unitary synthesis?
in life, I guess. So why would one need more than one query?
Um, I think there are algorithms. I'm not recalling any off the top of my head. But one thing that this is an idea from Will Kretschmer. If you think about like the task of implementing a permutation, like say that there's a random permutation on your input space, and your task is to unitarily implement like x to sigma of x or pi of x. That's something where it's like clear how to do it in two queries. You'll sort of like compute the x tensor sigma x, and then you compute again another query to like delete the x. So there is something where like it's clear that you can do it in two, and it's really not clear how you do it in one. So
Yeah, thank you.
Yes, so in your talk you had this definition that it's the same for every unitary, it's the same algorithm but with different oracle. Would something change if you allowed this different algorithm for every unitary?
that's a great question. Basically, no. This is like something that's known is that this formulation of the unitary synthesis problem, the one where you sort of demand a universal algorithm that works for any U, kind of doesn't matter. And the reason it doesn't matter is that like if you want to use a different algorithm for any U, you can make a query to the function and have it like write down a description of the different algorithm to use. So this sort of like universal framing is Walog.
Thanks. Yeah, let's thank the speaker again.